next we have our first invited talk. So I think we have the slides ready. So the talk is called Computation Models for FHE, Mixing Integer, Boolean, and Floating Point Operations, Applications to TFHE and Chimera. I've never known if I'm pronouncing that right. I think I'm about to find out. The talk is going to be a joint presentation by Nicolas Gama from SandboxAQ and Mariya Georgieva from inpher.
Wait, how does it work? Oh, okay. Nice. So thanks for inviting us. It's a pleasure to give a talk here about TFHE and Chimera. So actually Chimera, it was kind of a dream. Once we had the TFHE library and we saw different computation models like BGV, BFV, CKKS, we at some point tried to find a way of putting it together to do more computation. So that's what we are going to try to explain here. And of course, since it is not entirely implemented, it's also a call to the community to help us achieving this dream. At the beginning of FHE, so there was this thing that, so FHE, it's like running a program. So it's a program where you don't have any feedback on the computation you are doing while you are doing the computation. So in some sense, we can say that it really behaves like circuits. In 2009, Gentry came up with the bootstrapping idea that basically said that there was one crypto parameter you can set forever, and then out of it you are able to evaluate homomorphically NAND gates. And since then we know that the overhead between evaluating a plaintext circuit and evaluating in FHE, asymptotically it's bigger of 1 in time, in memory, in bits. So that's cool. The first well, maybe that was just it. That was the solution. We just had to wait for scientific progress to make it work and make this big of 1 practical. So yeah, here we have the time of 1 CPU cycle. 1 CPU cycle is around 1 nanosecond. And this is the evolution between 2009 and 2016 of the time of bootstrapping for 1 bit. So here I'm only considering a single bit bootstrapping, evaluating 1 NAND gate. So of course, in 2016, we were like, wow, that will be the solution. The curve will continue to go down, and at some point around 2020, maybe, bootstrapping will be as fast as plaintext. So that's a very simple idea that we would just have to take a program, compile it into a circuit. So a circuit can use binary gates, MUX, and, or, and once we have this circuit, we would just evaluate it homomorphically, and at some point, if homomorphic evaluation is very fast, then that would solve all the problems. Unfortunately, that's not exactly what happened. This prediction turned out to be wrong. Now we are in 2023, and obviously homomorphic encryption is still not as fast as plaintext. So the real curve looks like that. So we started to have speed up, like 100x speed up in GPUs, maybe 1000 in FPGA, then some optical systems that managed to replace the FFT by physical computation, and probably next year there will be the first ASIC that do homomorphic encryption with a target of achieving a factor 10x compared to plaintext. But all of that are material optimization. If we stick to CPU implementation, so of course there are still algorithmic progress on if you have many bits to bootstrap at once, or if you want to do bootstrapping for arithmetic in a high level, so like the talks we had in the first session. But if the problem is really to evaluate one single NAND gate and take the latency, well, the algorithm didn't evolve. It just followed more slow. So it means that on a laptop between 2016 and 2022, the running time of the gate continues decreasing. And for some obscure reason that I still not understand exactly, on a cloud VM, the 13 millisecond become 18 millisecond right now. So thankfully, in TFHE RS, Zama's team has included the AVX 512 to balance a little bit this increase. So, but yeah, overall, the curve has been flat until now, and there is still 1 million X gap between the plain text and FHE. So what does it mean? It means that if we still use this gate bootstrapping concept where you program into a binary circuit and evaluate all the gates, then even though it's the overhead is big of 1 in theory, we have this million X slowdown, and on a computer you can expect to run at most 100 gates in parallel, because on one CPU, even if you use all the threads and a big computer with multi-core, that's how slow it will get. Oops, what's that? So in practice, when you use gate bootstrapping, the only use cases that you are going to be able to solve are the ones that take a fraction in a second in plain text in practice. And for any other practical FHE operation, you need a plan B. And this plan B, I can summarize it by saying it's basically LHE to the rescue of FHE. So between fully homomorphic encryption and level homomorphic encryption, it's like between a continuous function and a uniformly continuous function. In FHE, it says there exist crypto parameters so that for all circuits, there is a way to evaluate it. And level homomorphic encryption, it's the quantifier is in the other direction. For all circuits, you can find crypto parameters that allow you to evaluate this function. So of course, you could say, well, the second one is already able to evaluate a lot of things. It starts with for all circuit, there is a way to evaluate it. So of course, the crypto parameter will degrade because it depends on the circuit. And if you look at the original bootstrapping ID, well, of course, if you want a counter example, so a function that is not LHE, just take a circuit that depends on the crypto parameter, like the decryption circuit, and you get the full loop. But yeah, that's not the point of Chimera. So Chimera is really the idea to combine the two IDs. So FHE and LHE are not mutually exclusive. It's not either you use FHE or you use LHE. Well, first, if you look at this definition, clearly FHE is included inside LHE, so they are not mutually exclusive, but really that's something that we have in practice. If the goal is to solve a problem, maybe there are a lot of things that you will be able to do using LHE, but if at some point you need to apply bootstrapping, don't hesitate to do that within LHE. Yeah? And so LHE basically is very good to apply massive arithmetic circuits, massive matrix multiplications. Bootstrapping is very good when it turns down to evaluating logic, lookup tables, or nonlinear functions, or converting from one format to another. And if we mix both, then we can start to obtain things that are really interesting. So now let's take the high-end user perspective. So the high-end user, well, we are researchers in FHE, so usually when we try to do some FHE, we are just going to take all the primitive and assemble it ourselves to make our own circuits. But in practice, a high-end user will prefer to have high-level pseudocode language that look like that, where it will be able to write its own function, and inside the function, we can have a lot of operations that occur inside. So we can have linear combination, modular arithmetic, floating points, SIMD, real-valued function, really a lot of things. And if we look at the history of FHE, all of these individual problems seemed hard at the first time we saw it, and over time, there were each time different paper that came out that solved one specific problem. So one paper for real-valued function, one paper for SIMD operation, one paper for modular arithmetic. But of course, the problem with LHE is that it is not universally composable. Usually, there is always something that is different between the input and the output of the function. So it can be the plain text space, it can be the ciphertext space, it can be even just the noise level. So the thing that is really hard is in this pseudocode is probably not only the arithmetic function that is inside, but also this new line character at the end of each instruction. So it does not just mean execute the second instruction after the first, but it also means that sometimes you will be computing result as an output of an operation that you need to put as an input of the next one. And this is the mathematical composition and something that is hard to achieve. So the idea of Chimera is to put all the capability of FHE together into a single world and try to draw all the roads and all the conversions that are between these different worlds. So on the top left, we have the BFV world. So it's the world where you can do SIMD arithmetic modulo, for example, a small prime. So you have element-wise addition, element-wise multiplication. You have some rotations. On the right, you have the CKKS world, where you can have SIMD operation over fixed points. So again, element-wise addition, element-wise multiplication, and a few rotations. At the bottom, we have the TFHE world with the Boolean circuits, the automata, branching programs, lookup tables. And if we look at the overall pictures, we see that there are always a way to go from one world to another. So if, for example, I start with doing an arithmetic circuit, but at some point I realize that there are still some operations that I want to do, but I cannot express it as an arithmetic circuit. It's not SIMD addition or multiplication. Then I can use this coefficient to slots or slot to coefficient to move out from the slots and obtain coefficient. So here I will end up with the bare representation of the things, which is an ideal sublattice of the torus. So the torus is an additive group. Of course, it doesn't have internally a multiplication. So usually when we talk about multiplication over the torus, we take one element and the second element. Usually it means the coordinate of the first element times the second. So dual of the first element times the second, or bit decomp of the first times the second. It's the same. And whoops, if we use this same coefficient to slots over CKKS, we'll realize that we end up in a very small area of the torus around 0. So it's a small ball. And basically, CKKS plays over the exponent of the floating point representation to make sure that we all the computation is constrained into this ball, and there is never any wraparound that can hurt the computation. So here we have all the key switching element or the trace algorithms. So once we have a coefficient of a polynomial that allow to move around the coefficient of the polynomial, extracting a coefficient, shifting coefficient around arbitrarily. Yeah? And if at some point we want to do some transformation that is absolutely nonlinear on the coefficient, so like rounding functions or something completely different, we have this functional bootstrapping or programmable bootstrapping that allow to apply completely arbitrary function over torus elements. So let's say, for example, that I don't know. Yeah, let's say I want to compute homomorphically the number of weekends I've spent on building slides, and I don't know, assign a different score to time spent on Saturdays and Sunday. So maybe I will need to begin my computation with things that are modulo 7 to be able to convert a date into the day of the week. And so here, maybe the computation will start in the BFE world modulo 7. And then once I've extracted the fact that it could be a Saturday or Sunday, so 6 or 0 modulo 7, then to each day I want to assign a different score. So maybe Saturday that will be score 2 and Sunday score 7 because it's much more painful to work on a Sunday. So then for this kind of operation, it's absolutely nonlinear. So here it will be the domain of the functional bootstrapping to do that, to convert any 6 modulo 7 into 2 and the other into another score. And then this functional bootstrapping will bring me to the CKKS world where I will be able to add my floating point score. If now I want to, so I don't want to treat my scores as floating point, but maybe as big integers. So like something modulo, I don't know, using RSA modulus. So there is also a way to use, yeah, there are ideal lattices over the torus that are isomorphic to computation modulo big integer. And I think there was a paper around 2008, probably by Kim Lane at Microsoft, that gave an example. So here, even though the computation modulo 7 and the computation modulo the big integer seem to be on the same part of the map, they correspond to a different lattice over the torus. So it's like there were parallel universe, one that is modulo 7 and one that is modulo the big integer. So again, it's a different country, so it's programmable bootstrapping that will make the transfer between one and the other representation. Another example maybe, if we look at machine learning algorithms, usually in a machine learning algorithm, there will be a huge matrices arithmetic, matrix vector arithmetic that we do when we compute a model, but at some point there is always some nonlinear decision diagram that we need to apply. So what happens is, out of all the coefficients that we have on the matrix, usually we'll start extracting some meaningful features, compress it, and over the smaller set of features, then try to apply some more complex algorithms, like, for example, tree boosting or decision trees or any circuit like that. So if we try to evaluate these decision trees on a large-scale arithmetic, the problem is that we'll lose all the time that we gained for the heavy arithmetic. to try to evaluate this small circuit. So instead, once again, after we have computed this heavy arithmetic and extracted the feature, we can use the functional bootstrapping to move out to the TFHE logic unit, do the decision tree within TFHE, and once we have the new parameter set, use this programmable bootstrapping to come back to the arithmetic world and continue the operation. So there are a lot of things that we can express using this map. Now, let's try to take the point of view of the compiler. So, when we build a compiler, the idea is that we want to have a virtual machine, and we want to abstract away all the complexity of the underlying representation. We just want to have some simple criteria of what the elementary operation is doing and what are the parameters, how it can be parameterized. So if we look at the property of a leveled homomorphic encryption ciphertext, we have, of course, a message. So the message can be 1 bit, 1 integer, a vector of float, and we have a homomorphic budget. So homomorphic budget, there are many different equivalent notion, the noise rate. Something that is actually good is to take the logarithm of the noise rate. So here in this presentation, I will call it points. Sometimes we speak about levels, homomorphic levels. For example, in CKKS, BGV, so when the arithmetic model is addition or multiplication, usually we like to count the number of multiplications. So in this case, we can say that one level is about 30 points. But the nice thing with this scale with points is that if we move out of the addition, multiplication, arithmetic and start to include logical circuit inside, it's better to have something a graduation that is smooth. So yeah, these are some examples of ciphertext and how fast an operation can be. So basically a level 0 ciphertext. So a ciphertext where the noise is exhausted, that can only be served as encryption and final results. Usually computation on it will be very fast. Same for level 1 and 2. But if you increase the level too much, like level 10, so 300 bits of noise and moduli, then we start to have arithmetic that is very slow. So the rule of thumb is the bigger the ciphertext, the slower it gets. And the nice thing is that we can just take all the operation that we have, so slot-wise product, sum, rotation, and map it in terms of how many points it requires to perform this operation. So once we have a circuit that uses all of these operations, each operation has an effect on the number of points, and then for each ciphertext we have to assign at which point it will be encrypted, with the rule that the number of points should never go below 0. If it goes below 0, it means that your circuit is wrong and the result will never decrypt correctly. And the notion of point can also be applied to bootstrapping. So we can take all the different bootstrappings in the literature and each time translate it into what it gives in terms of plain text space and how many and what are the requirements in terms of noise. So some bootstrapping can take a level 0 ciphertext and just raise a number of points. Other bootstrapping will require a certain amount of noise at the input of the bootstrapping and will raise a number of noise. So it means if you have done too many operations and you are already below 180 points, you will not be able to apply this bootstrapping anymore. So it's only the end of the computation. and the gate bootstrapping goes between 0 and 1. So yeah, so arithmetic that works really well. And the concept of noise, so it can also be applied to non-arithmetic circuits. So like, for example, this MUX gate based circuit. So in a MUX gate, like the one that is used in the GSW ciphertext, what it means in terms of point is that one of the inputs of the MUX gate has to be a higher, at a higher level, like 30 points, and then the two other inputs of the noise has p points. And the good thing is that if the control bit of the MUX has more than 30 points, is 30 points higher than the other entries, then the MUX gate will preserve the budget, which allows to do a long chain of MUX gate without losing too much points. So this is the one that is applied in TFHE for example, lookup table. So if I have a table, a lookup table and MUX gates, well, how do I combine the gates to obtain the outputs? I'll just combine them like that. So the inputs are on the top, the output is here. I can do much more than lookup tables, so I can also evaluate automata. So a finite automata is some graph like that where you read a word. Every time you read a letter, you follow a transition. And here in a finite automata, you will try to answer if you are in an accepting state or not. Or you can have weighted automata. So whenever you read a letter, you will add the weights that are on the path. And again, evaluating this automata is just piling MUX together. So you can evaluate automata. So of course, deterministic automata, they have a big problem, is that whenever we want to do something meaningful with a deterministic automata, the number of states tends to grow exponentially. So it's very important to be able to compose small automata together. And if we do a naive composition, every time we compose an automata, we'll have to increase the level by 1. So one other thing that TFHE allows is this gate bootstrapping construction that is takes a level 0 ciphertext and raise it to level 2 that can be used as input to the next automata. So we have a composition like that on level 0 and 1 that can be used together with Boolean circuit to obtain a very non-trivial logic. So yeah, I guess that's it for the composition part of TFHE, and now I will let Mariya explain in more detail how the ciphertexts are built.
Thank you very much, Nicolas. Yes, in the last few minutes, I will explain how what there's mathematically in all these Lego bricks. Just I should learn how to work with that. Okay, starting first by some definition. We defined the rings of polynomials with integer, real, and complex number, and they are well defined as rings. Why? Because they are groups, and also the multiplication is well defined here. What happened if we are not on the real, complex, and integer polynomials, and if we work with the torus? In this case, we have the addition that is well defined. That means the torus is a group. We also have the external product with an integer number that it's well defined. That means we are in the Z module, but the internal product it's not defined. Why? Because if we take an element from the torus, for example, 0, that can be expressed or by 0 or by 1, and in this case our internal product it's not defined. That means we are not in the ring. That's exactly the same with the polynomial version. That means TNX, the torus polynomials. In this case, we have an Zn module. That means the external product by integer polynomials are well defined, but the internal one not. In the TFHE scheme, we have three different kinds of ciphertext. The first one is to encrypt an element from the torus. The second one is to encrypt an element from the polynomial, the torus polynomial. And the third one is the TRJSW that encrypt an element from ZNX, so with a small norm. And now if we work with all this kind of ciphertext, we can perform the linear combination. With the first two, the product it's not allowed, and with the TRJSW, we have the internal product between two ciphertext. But we also, due to the Z module structure, we have the external product between ciphertext of TRJSW and TRLWE. What's the important part here? It's that the noise grow with the norm of the first plain text, that means the one encrypted with TRJSW. And if the norm is small, for example 1, the noise propagation is linear. Now what about the internal product on a ring warning with error? If we express the plain text multiplication using the decryption formula, we will obtain a polynomial of the secret key S of degree 2. The term of S2, there are lots of methods in the literature with dedicated linearization key switching techniques that allows to remove this S2 term. But in fact, we can also use the ciphertext of a ring GSW to provide the multiplication by the secret S. Now what about the meaning of all other terms? B1, B2, the multiplication, as we said, we cannot do directly an internal product between elements of the torus. That means we should lift them first in the real polynomials and add some special message space restrictions to make such a product meaningful. Now we will sum up a little bit the homomorphic operations hierarchy using this kind of ciphertext. Starting with the ring warning with error, we can perform any small integer linear combination. And here we see that for any A in Z and X, public of course. Now, using the ciphertext of RGSW, we can also perform an external product with this time A secret, and we have different cases depending of this secret A. If A is a binary value, if we encrypt 0 or 1, we obtain all operations as Nicolas showed just before, as the semux, the selector, the blind rotate, and all automata evaluation. That means that gives us the TFHE gate API with the evaluation of the individual bits, so nonce, OR, XORs, and etc. And now what if A is the secret key? That means if we take a polynomials in S, as we said so before, we can perform an internal product, and that unlocks us two other API depending of the plain text space, the sublattice, or if we are in the small bow in the torus, we will obtain the two other API, the BFV1 that gives us the slot arithmetics over the integers, and the CKKS1 that gives us the arithmetic on fixed point arithmetic. Here, just to summarize the different models of computations, that means we obtain the three different API, the TFHE that allow us the evaluation of binary circuits, lookup tables, deterministic automatas. We obtain also the integer arithmetics over the slots and the approximate or the fixed point again over the slots. Now with the Chimera work, we show how we can unify all plain text space over the torus, and also we show how we can switch between the ciphertext representation. We will start by the second problem. That's the easy one. That means coefficient, how we can switch between coefficient and the slot packing. The coefficient packing, it's just we encrypt a plain text per coefficient. The slot packing, we used the unitary route to evaluate our plain text unit. Sorry. To obtain the different slots. The good news is that exists an morphism to switch between the two representations, and this morphism it's just an Vandermonde matrix that allows us to do this coefficient to slot switch. Now, if we are on the complex number, we have exactly n complex slots. If we work on the real one, we have n over 2 complex slots. And if we are on the integers, we should add some additional constraints. Now we will see the first problem that we discussed, how we can map our plain text on the torus starting by the integers. We defined the polynomial over the integers modulo p. That's the ring of polynomials with integers modulo p, and if xn plus 1 has exactly n roots modulo p, that means we have this isomorphism property, and in this case we can just represent our plain text space composed by the exact multiples of 1 over p. That means our new plain text space will be the red point on the torus. Using this plain text space, the plain text addition, it's just a classical addition. The plain text product, we use the Montgomery style product. That means we will first lift our plain text over the real polynomials and multiply by p. Here we have a small particularity. When we work with this product, and when our elements are exact multiples of 1 over p, when we lift on the reals, and we can use any lifts, that means any integers here, and again we will obtain the exact product. But in the fully homomorphic encryption, we never works with the exact plain text. We always add a noise, and with the noise, the product, if we take a small representant on, that means small lift on the real numbers, we keep this property, and we still obtain a result that it's really close to our multiplication. But in the case when we take a big representant on the real numbers, for example, as in my example here, we will completely lost the information. What that means? That means we need a small representatives of the plain text to keep the result correct. For that, we should lift the ciphertext to the small representatives in the RNX and keep the coefficients in the interval -1/2 and 1/2. Here for the homomorphic operations, the homomorphic addition, it's the classical one. For the homomorphic product, we will use again this formula, the Montgomery one with the decryption expression. We obtain an polynomial of the secret key S of degree 2. That means now my ciphertext product can be expressed using A and B. That means the red and the blue part. And to remove the term S square, we will use the encryption of the TRGSW, the encryption of the S, and my internal product of two ciphertext will be expressed by this formula. Of course, as I said before, we should give a meaning of the terms AI times A2, BY, B2. In this case, we will take them as a small representatives in the RNX. Now, what about the fixed point numbers? First, what's exactly a fixed point? It's exactly as the floating point representation. We have an mantissa, we have an exponent, but the difference is that the exponent, this time it's public, and that means much more fully homomorphic encryption friendly. Of course, when we take the exponent public, we have a risk of overflow or underflow, as in my example here. Another particularities is that with the fixed point representation, it's not so linear to do even additions, because giving the mantissa and the exponent to compute the addition of both fixed point numbers with raw bits of precision, we need some nonlinear operations as right shift rounding, which are not linear. Now we will show how we will map our fixed point numbers again over the torus. We will use a small interval on the torus. We will use this notion of levels and say that our new plain text will be this continuous interval. Now to perform a product, we should still lift the numbers over the real numbers, and the function of the lift is represented by this periodic red function. In the case when we really use numbers that are close to integers, that means in small interval, we can approximate this periodic discontinuous functions by a continuous one, for example, by the sinus or other Fourier expression. And in this case, we can use it to express the lift and the multiplication. But the problem is that the sinus can be approximated by a polynomial. That means to evaluate a sinus, we need to evaluate a polynomial that we will use again at products. And we will have this problem of chick and eggs, in which to do a multiplication in the continuous approach to keep the interval not, how to say, constant or even reduced it, we need to have another way to evaluate multiplications. And that's the discrete approach. That means this time our plain text space, it will be not the continuous one, but we will take a discrete version, again in a small interval of the torus, but this time we will use exact multiples of 1 over q. And that will bring us on the ring 1 over q ZNX modulo z, and we can use the exact Montgomery product just as before, and the meaning of all my multiplications terms here will be well defined because AI and BI will be exact multiples of 1 over Q. The problem of this approach is that it's a leveled approach. What that means? When we use this multiplication, every time we will blow up our interval and we can apply it just some limit number of times. But the good news is that we can combine the discrete and the continuous approach in a way where we need to evaluate the multiplication. We will start by the continuous one, and to evaluate the continuous one, we will use some discrete in a way to evaluate the sinus, for example. And that's all from us. Thank you very much for the attention, and you are welcome for questions.
Okay, so any questions? Again, don't be shy. Someone must have a question.
It's the lunchtime. It depends if it's the French or Bulgarian accent. But Chimera, I don't know what's the right one.
I have heard both. Chimera,
Chimera in French.
Okay, then I have a quick question. What's
Yes.
the status of implementation? Is there a private implementation?
We have some experimental implementation that we did a few years ago, and we use it for one of the I- competitions. That means we implement some of the needed bridge and operations of Chimera. But that's a really good question. I think we should retake this work and to do a real good implementation, stable and not experimental one. And everybody is welcome to help us with this task.
Thank you for your insightful presentation. I have one real question and side question. And real question is, we want this convergence to be not just efficient, but also like practically meaningful. So I'm wondering, like, what's the real application that requires like conversion between CK case and FE?
Between CKKS and BAV?
FE, yes.
we actually don't know.
Okay. And my side question is, as someone who with a math degree, I mean, torus usually refers to S1 times S1, but it's S1 in your paper, but you also use figures like over S1 times S1. So S1 is like R mod 1 circle. So I was just wondering if I'm misunderstanding something, or you did on purpose.
No. So it is what Mariya explained. So usually it depends on the encoding. So on the BFV, usually we'll have an ideal sublattice, and the multiplication means the dual of the first element times the second. So dual in the sense the coordinates, integer coordinate of the first element on one particular basis times the second one. So it's really decompose the first one and multiply by the second.
Makes sense. Thank you.
So first of all, thanks for your presentation. I have a question. Last year was a paper by Alibaba Open Pegasus, and they claim they are better, like 1 order of magnitude. They are faster and something like that. And can you name some advantage of Chimera compared to that work, or any disadvantage of that work or something like
The
that?
reason it's probably we don't know. Chimera was done 4 years ago or even 5 years ago. That means probably there are improvements on this work we should follow.
They have some conversion between CKKS and FHEW, and they have some claim they are better, like 1 order of magnitude, maybe.
Yeah, we should follow up on that.
Okay.
At the time of Chimera, so in 2018, we only had the functional or programmable bootstrapping ID to do the conversion coefficient by coefficient. So if there are some more packed way to do it, then that can be another approach.
Okay, yeah, thank you.
Okay, let's thank Nicolas and Mariya again.